Today in this video, we're going to be talking about counting. Counting in the context of being able to count for the sake of probability. It seems kind of silly to just say, here, we're gonna learn how to count. And it's not that we're learning how to count, it's we're going to be looking at some different counting methods. So in probability, the finding of the probability of anything has to do with knowing the numbers of ways things can happen. So for the probability of an event is the number of outcomes of that event divided by basically all the possible outcomes that could possibly happen, the outcomes of the sample space. The problem really becomes is counting these outcomes, because some of this gets kind of complicated fairly fast. So we're going to cover some of the three basic counting principles. We're going to cover the fundamental counting principle, permutations, and combinations. I would say you've probably seen this stuff before. At this level, you've probably seen it a couple of times. So hopefully a lot of this is just reviewed for you. So I might be going a little bit fast, but you have seen these ideas before. Let's say I throw this scenario at you here where we're looking at the ways that maybe a license plate is put together. And I say, well, take California here. How many license plates can they make with this particular configuration before there's more cars than ways to make a new license plate? So the number of ways. Because then if I say, what's the probability of this particular license plate? Well, you'd have to know the number of ways. And this is based off of our first fundamental counting principle of, well, how do you combine? I mean, I know we got some letters here and we've got some numbers here. And you can kind of see that with a lot of different license plates. You got letters and you got numbers, and sometimes they're mixed in, sometimes they're not. Depends upon the configuration. Like here's a more modern California license plate. That's an old one there. And here they're mixing in letters with the numbers. And that can actually change things quite a bit if they do that. But it gets a little bit complicated on how do you count those ways. And this particular method is going to be what's called the fundamental counting principle. I'm going to go back to the license plates in just a second here, but it's saying if that there's a couple of events. So A and B are two events, and this could be 3, 4, 5. It could be however many events. In the case of the license plates, it's more than two. If one of the events A has a certain number of possible outcomes and the next one B has a certain number of possible outcomes, to get the total number of possible outcomes, you have to multiply them together. And that's what's known as the fundamental counting principle. The old basic Algebra 1 example given typically has, I got a couple pairs of pants and I got 3 shirts. How many outfits could I put together? And of course, you could draw a what's called a probability tree. And you start off with one of the outcomes, that mean pants. And I could have done this with shirts first. It really doesn't actually matter. And you list off, okay, how many ways can I put all this? And actually, if you start counting, you'll see it here. From this pair of pants to any of the 3 shirts, there's 3 ways. But from this pair of pants, there's a different 3 ways. So you get a total of 6 ways. Typically, they're drawn more organized, something like this, because this can very, very quickly become really hard to distinguish ways out of. But here you can see it. There's 6 ways. Well, of course, if I just taken 2 multiplied by 3, I would have gotten the 6. But this would be the sample space showing you everything that could possibly happen. So going back to the license plates, to cover how many here, well, it depends on whether you're considering, let's take this California one here. Let's say that there's no repeating with these letters or with these digits. And sometimes there might be. Maybe you can have repeating. That's part of what would be the law at that current point in time on how they've agreed to make their license plates. But let's say that there's no repeating. In this spot, well, obviously there'd be 26 letters of the alphabet that could go there. This one, if I'm not going to repeat, well, then there'd only be 25 left, 24 left. And then with the digits, I'm going to have 10 digits going from 0 to 9. And since that 3 there's been used, I only have 9 ways I could do the next. And I would have 8 ways to do the next. So I'd go 26 times 25 times 24 times 10 times 9 times 8, and that would give me, it'd be a big number, but that would give me all the ways that I could make license plates with this particular configuration. And of course, then states can do things like, well, maybe we'll put the numbers first and then the letters. Of course, then they'd have to double it because that would double the possible ways that could happen there. So you could play with those repeating. It'd be 26, 26, 26, 10, 10, 10. If they did allow for repeating, and maybe they have a limited number of repeating. It all depends. But that's how you'd go about calculating something like that. So it's going to be based off the fundamental accounting principle. So here would be an example. Let's say that somebody goes into a test and it's got 20 questions, and it's one of those bubble sheet ones where you have 4 choices for each one of the questions. And they're going to, for some crazy reason, they're going to take it what I would call idiot bingo style, which totally just guessing each of the 4. How many ways could they possibly fill this thing out? Well, you could do it this way. In the first question, there's 4. And the next question, there's 4. And the next question, there's 4. But as you can see, this is going to be a lot of number punching on your calculator there. You could also take advantage in situations like this where it's the same thing over and over and over, being multiplied by itself many, many, many times. Exponents. Just take advantage of the exponents. 4 to the 20th power. And as you can see, it would be a huge number. Now, this is just a counting method. This is not specifically geared to probability. If I then wanted to say, hey, what's the probability of them getting the one correct mixture of answers that gives them 100%? Well, then it'd be just 1 out of this very, very, very large number right here. Here's another example of the fundamental counting principle. Let's say these 5 different cars have come and they're going to have a race, and they're showing up one at a time here. And of course, there's going to be 5 spots. There's the farthest to the left, second farthest from the left, all the way going to the farthest on the right. If they just showed up at random, how many ways could these 5 cars possibly line up? Well, the first car, when they show up, they would have their choice of 5 different spots. They'd have 5 ways to do it. But then the next car, well, 1 spot's going to be taken. So then they would have 4 ways. And whether it's this spot or another spot, but it'd have 4 ways to choose. And then the next car would have 3, and then the next car 2, and so on and so forth. The last car wouldn't have any choice. It'd be the only one there. You could draw out the sample space. Here, I got sick of doing it. I didn't even get close to all the different ways I could do it. Or we just use multiplication. Now, in this case, you can't just use exponents, though. It's not like it's 5 to the 5th or something like that, because you got to go 5 ways times 4 ways times 3 ways times. And so there's a different tool that we have in mathematics when we are going to be multiplying by consecutive integers going down by 1. And this is the idea. By the way, this is how many ways there are. So you can tell that's why I got sick of drawing that out. I knew I wasn't going to go that many ways out. But you might recognize this 5 times 4 times 3 times 2 times 1. And that's the idea of what's called the factorial. I know it's an exclamation point. It does not mean to yell it when you say it. It just is a mathematical symbol in this case for taking consecutive integers that are going down by 1 and multiplying them all together. And by the way, I don't know that I have this anymore, but factorial of 0, if you do 0 factorial, has been defined as being equal to 1. Just in case that comes up, it's a pretty rare question, but I've had students ask me that. Wait, what if I multiply by 0? Well, of course, you multiply by 0, it wipes everything out. So we just have defined in mathematics that 0 factorial is going to be a 1. So here would be an example. You want to arrange 4 books on a shelf. How many ways could you do it? Well, of course, it's 4 times 3 times 2 times 1, just like with the cars. And you end up with 24. There's the definition. Oh, and by the way, yes, excuse me, I did have this here. By definition, 0 factorial is 1. Now, on your graphing calculator, you have a factorial button. If you hit your math button and then go over to, this is probability. We're going to see a few of these things come out of here today. Then the fourth thing down is your factorial. We've also got in here this is going to be one we come back to today. That's going to be for our permutations, and we're also going to use this one today. That's for combinations. And so you'll be visiting this probability button quite often. We already looked at in a different video lecture the random integer. That was right here. So there's quite a few of these buttons under probability that we end up using. So let's talk about the permutation. Permutation, and if you're taking notes, this needs to go in your notes. Permutation is when the order matters. Okay, so let's say that this racetrack here is one that actually is going to go to the left. Just a great big oval. This would be the preferred spot. So the first person that comes, they're going to want that spot. It's preferred over anything else, and so the order matters here. If you know anything about racing, this person covers less distance if they're farther to the left if it's an oval racetrack. So this would be the second preferred, third preferred, fourth preferred, and the one nobody would want would be this one. So the order matters if I change it to that type of scenario. Permutations are used for that. Now, in this case, this was a permutation. In this definition, I know we talked about the fundamental counting principle, but if the order matters, then the fundamental counting principle is technically a permutation. We've got a couple notations for permutations. They both mean the exact same thing. And in this case, I'm actually describing this situation here. The P is for permutations. Inside the parentheses with this notation is how many things are there. In this case, there's 5 cars. And how many, let's say spots. We'll just use that for now. How many positions or spots were there? Well, there would be 5 spots or 5 positions. So 5 permutations taken 5 at a time is how you would usually say that. A permutation of 5 taken 5 at a time. Because it could be, let's say we had 9 cars show up. It could be a permutation of 9 taking 5 at a time. 9 cars show up, but there's only 5 spots. So not everybody's going to get one. This notation means the same thing. This is always going to be the bigger number. So let's say there was 9 cars that showed up with 5 spots. This one would be a 9. In this notation, this is the bigger number. They mean the same thing. This is the one you'll see on your graphing calculator. And you're going to enter these by first putting in the big number and then choosing permutation and then the smaller number. It will not be a simple just factorial if there's a bigger and a smaller number. It only happens to be the basic fundamental counting principle with a factorial if the numbers happen to match. Okay, so let's have it not match. So 3 cars are going to be able to race out of the 5 cars that come. So there's going to be 2 spots that are not available. But there's still going to be 5 cars that show up. So what happens mathematically is you get that, well, there's 5 cars. 5 times 4 times 3 times 2 times 1. But 2 cars aren't going to get a spot. And so we'd have to look at, of course, the factorial of that. And these two actually cancel out with those. And so it ends up just being that it'll be only 60 ways that you could do it if there was only 3 spots, but 5 cars showed up. Again, this is how you would write that. Big numbers always first. Permutation. So 5 permutations, choosing 3 at a time. Notice I'm kind of saying it a little different multiple times. There's not one necessary way to do this. There is a formula for doing this calculation. And basically it's the big number factorial divided by the big number minus the small one, and then factorial. Now, you probably won't be using the formula at all because we'll have our calculator to do this. And I already mentioned that you had permutations in there. When you go to enter these on your calculator, you would put the 5. And then you'd go to your math button, your probability button, and you'd choose permutations. As soon as you hit enter, it's going to kick you back out to the main screen. That's when you would tell it the small number, 3. And then you'd hit enter, and it runs it through the formula for you. So the formula has been programmed already into your graphing calculator. This question here comes up sometimes, and I want to cover it only because it's shown up on ACT questions. and some people might be wanting to retake or to take the ACT. And it has, this one I've always found confusing myself when I was younger, has to do with electing positions. And it wasn't until I realized, okay, so limit the scenario here. They got 11 members. They're going to elect a president, a vice president, and a treasurer. How many different outcomes could there be? I used to confuse this problem with combinations, and I know I haven't gotten there yet today, but when I get there, I think you'll understand why I maybe would confuse these. Until I realized that order does matter here, because people typically prefer the idea of president. And that was what I confused. I was like, well, I don't know, they get stuck doing all the responsibility. I'm not sure if I want to be president, kind of thing. In this situation, you would look at this as the preferred choice, president, second preferred choice, and third preferred choice. And so the order would matter when they come to vote those in. So this would be a permutation. It'd be 11 choose 3 permutations. Notice I said that a little different again. There's more than one way to say it. And it ends up being 990. Pretty simple to do with your calculator. I would, by the way, maybe pause this and try it to make sure you can get the correct answer out of your calculator. This would be a good time to try that. I think I'm actually going to skip this one. It's another very similar thing. Well, I'll just go through the why I choose permutations on this one. It's got 4 spots available, 7 members wanted, and there's going to be some preferred positions on the football field. So order matters. That makes this a permutation question. Okay. So I want you to think about this. I've got 3 letters, A, B, and C. I want to put how many ways can I arrange them where I'm taking 2 at a time? Okay, so I got A, B, I got A, C, B, A, C, A, B, C. Well, it looks like I'm going to have 6 of them, okay, which you can count them, or of course it's a permutation, 3 permutations, choosing 2 at a time. And I end up with 6. But what if I say now that the order doesn't matter? So like then A and B and A, well, let's say order doesn't matter. Then they'd really be the same thing. And so I'd be double counting here, so I could eliminate that. And A and C, well, they're the same thing too. So I could eliminate one of those two. And then I've got B, C, and CB. Well, they're the same thing too, so I'm going to eliminate one of those. Notice how I end up with a smaller number of arrangements if the order does not matter. And that's what's called a combination. Okay, a combination is when the order does not matter. That should go into your notes. Combinations, the order does not matter. Permutations, the order does matter. I used to get these guys confused, mostly because when I was in high school, we had locks in our lockers and we called them combination locks. And of course, the order matters. Until I realized finally, or actually somebody pointed out that they were misnamed, probably by somebody that didn't really understand probability that well. They should have been called a permutation lock because the order really does matter. You don't get to choose which number comes first out of the 3. Typically, it's 3 numbers on your lock out on your locker. But the order matters. You can't just kind of do it willy-nilly. You have to have them in the correct order. So they should have actually been called a permutation lock. But again, most likely the manufacturers weren't focused on the math vocabulary. They just called them a combination. There is, again, a formula for this. It's very, very similar to the permutations. The only difference is that small number, the denominator gets multiplied by the factorial of that. Other than that, this left side here, that's the same exact thing as the permutation. You will get smaller answers because if you're dividing by a bigger number, you're going to get a smaller value to the outcome. But again, this is on your graphing calculator. You probably won't be using the formula. I just wanted to point out the fact that you get a smaller number with a combination than you do with a permutation. Same spot in the math button under probability, except it's choice number 3. You have to first put in the big number, then you go to your math probability, you select this, it'll kick you back out to the main screen. Then you put in the smaller number. It's always big first, then small. and it'll give you the value. If you want to pause it here and try it, this one here, you could it should end up being a 3. You could pause it and make sure you can get that out of your calculator correctly. All right, let's take a look at this here. You flip a quarter 4 times. What is, now I want to talk about the probability. What is the probability of getting 3 heads? Well, this here's a probability tree right here. And notice I didn't say when you got the heads. I didn't say that the first 3 had to be heads or the last 3 had to be heads, or I didn't specify that. So what you could do with the tree is you could just start counting them out. Okay, so I'm going to get 3 heads. So I got heads, heads, heads. Well, this one works. This one would not, because it'd be 4 heads in a row. I could go heads, heads, tail, heads. This one would work. This one would not, because it'd have 2 heads. So on and so forth. I'm not going to go through the whole list, but you could go through and you could cross off or circle the ones that are. And what you'd end up with here, you got 1, 2, 3, 4. Okay, so there's going to be the 4. There's going to be 4 ways of getting that. And so then the probability would be 1 out of those 4. Well, you can do this with combinations. This is a combination thing. What you would want to do here is just go 1 divided by. So that part you'd have to know to do on your own. 1 divided by a combination of 4 choosing 3 combinations, or 4 combinations choosing 3 at a time. And you know, your calculator won't say 1/4. It's going to say 0.25, but you just have to go divide it by that. Or if you want, you could run this through your calculator and get your 4, and then just go 1 divided by your last answer, and you'd still get 0.25. So you can do probability questions. This is how it's related to combinations. And the same would be true if it happened to have been a permutation. I kind of want to focus on the word problems only because it gets hard to decide, hey, wait a minute, is this a combination question or is this a permutation question? That is the hard thing to decide here. So let me go through this one. Bill wants to buy 5 donuts and he has 10 different kinds to choose from. How many ways can Bill put together a combination of 5 donuts? Okay, well, in this case, I sort of gave it away. I shouldn't have it phrased combination. Sort of gave it away there, but the reason it is a combination is because if you ever bought donuts, you pick up a box and you start selecting the donuts you want, but the order you put them into the box to go pay for them really doesn't matter. And so it is a combination thing. If for some reason the order you put the donuts into the box mattered, that would make it a permutation question. But this is definitely a combination question because how you put them in the box doesn't matter. The actual calculation is not difficult. Again, you just grab your calculator. You got your big number, got your small number. It's a combination because the order doesn't matter. Get your value right there. That's not the hard thing with this stuff. The hard thing is deciding combination or permutation. Let's take a look at this one. To win the Powerball, you need to match 5 numbered white ping pong balls. They go from 1 to 69. No particular order, so you should already have an idea of where I'm going to go with this. And then there's 1 red ball. That's the Powerball. Those are numbered anywhere from 1 to 26. And this is actually a machine where these ping pong balls come flying up. They used to show this on TV. I don't think they do anymore. But by law, this actually has to be done with a machine, not a simulation. How many number combinations are there for the white? Okay, well, it's kind of given away here. Again, I'm sort of giving away the answers, but it is a combination because the order they come up in does not matter. So there's 69 ping pong balls taken 5 at a time. So if 69 combinations, choose 5. Big number, over 11, what do we got there? Million different ways that could happen. And then for the Powerball, the red one, well, it's 26 ways choosing 1 at a time, 1 combination. Well, that's actually just 26 then. Anytime that this is a 1, it's just going to be the big number. Now, we got to put these together here. Sometimes when you talk about probability, you're going to have to mix and match our different counting methods. And that's what's going to happen here. I've got the ways that the white balls, ping pong balls, can be brought up. I've got the ways that the red ping pong balls can be brought up. But now I got to combine them. And if you go back to the fundamental counting principle, says if you take the number of ways that the first event outcome can happen and the number of ways the second event's outcome can happen, you have to multiply them together to get all the ways it could possibly happen. So back to the fundamental counting principle, over 292 million ways that could possibly happen is how you would do that. And then of course the probability of having a winning ticket would be 1 over that, one winning ticket. Now if I had 5 tickets, it'd be 5 over that, so on and so forth. So this isn't directly a probability question, but it could very easily become one, and I just want to point that out. Poker hands. Okay, so let's take a look at this one. A standard deck of cards consisting of 52 cards. In poker, you're dealt 5. How many different poker hands are possible? Here again. Is this a combination question or a permutation? And this time I didn't give it away. So I want you to think about that. What would it be? Combination or permutation? Think about when you've played cards. Does the order you get the cards? So somebody's dealing out cards. You get dealt 5 cards. You're picking them up. You're putting them in your hand. Does the order you get them in matter when you're starting that game? Well, if you think about that, you're probably going to realize no, because you know what? The average person, you watch them get their cards, what's the first thing they do? They start to rearrange them as they get them. So the order they got them in doesn't really matter. They're going to rearrange them anyways. And so this, since order does not matter, is a combination thing. And so it's 52, choose 5 at a time combinations, which is about 2.5 million plus change different hands that you could get. So of course now you can talk about, what's the probability of getting such and such and such, out of all the number of hands. Then you've got to look at, the ones that you really want for winning. You have to look at what they are. Okay, kind of switching gears here. This is another counting method thing called the labeling problem. When some items are identical to others, so you really, really cannot tell the difference. The author of this text calls this the permutation rule. But when you cannot tell, this is the big thing. If they're identical, I cannot tell the difference, then you're going to use this. I call it the labeling problem or the labeling rule. He calls it the permutation rule. It doesn't matter. And it's just big formula. Give me a second here because it's easier to explain what the formula is doing with an actual example. Let's take that you've got some of those kids' blocks. When you really, really little kids, little wooden blocks, they had a letter on each of them. And you want to take a bunch of the blocks and you want to arrange the word Cincinnati. And you go, how many different ways can I arrange this? Well, the truth is, like this N here and this N and this N, it doesn't matter which block you stick in there, it just has to be the letter N. And so that's the idea of being identical. And so I don't necessarily have to multiply by, 26 letters here and here and here because, these 3, they could have been mixed and matched and it doesn't really matter. Same with the letter C's. That's why I picked this. And the letter I's. As you can see, the only ones here that are actually distinctive to themselves is the A and the T. Okay, so then this rule up here. What you do with this rule is you count how many there are. And that's going to be the N. Here, I'll just show you what you've got here. In this case, there's 10 letters in the word Cincinnati. So that's going to be 10 factorial. Then you count how many C's there are. Okay, there was 2 of them. That'll be a 2 factorial. How many I's? Well, there was 3 letter I's, so there'll be 3 factorial. N's, there's 3 factorial. So however many times they repeat, it's that factorial. And then down here, you're going to multiply all these together. So the top is how many things total, factorial. The bottom is how many times each thing repeats, that number, factorial. But you got to find the product of all them once you've got them. Then you run it through your calculator to get the number of, and the term is distinguishable. So what that again means is, like, if I switch these two ends, I can't tell, you can't tell, it's indistinguishable. So how many distinguishable ways can we arrange them? Obviously, if I switch the N and the A, well, yeah, it's not spelt correctly then, so that would be distinguishable. People would know that I messed it up. Okay, so that's typically the way these are worded. This is called a labeling problem. Like I said, your author used the term permutation rule, but that's how that is. If you put this in your notes, you make sure you give yourself some explanation on what those things mean. In fact, you should put that in your notes, but also give yourself explanation. Okay, here's another example of the permutation rule or the labeling rule. How many ways can we assign 6 drivers to the 4 red Mazdas and the 2 whites? Okay, so it's hard to tell as they go down. There's a red, a white, a red, a red, a white. You know, these little, like for parades or something where they zip around with those little Mazda Miatas. Well, the red ones you really can't distinguish, and the white ones you can't distinguish. And so what it's going to be is you've got 4 and 2 is 6, so it's going to be 6 factorial. How many total factorial? Divided by, well, there's 4 red ones. I can't distinguish between the red ones. And there's 2 white ones. I can't distinguish between the white ones. And so I'm going to run all that through my calculator. Ends up with 15. 15 ways that we can distinguish. Obviously, if you switch the red and the white ones right here, you'd notice the difference. You can also do this with combinations. It's just a different approach. Most students, I think find this formula easier to remember than this. I'm just showing you there's another way you could do this here in combination, no pun intended, with the fundamental counting principle. You do combinations of 6 choose 4 for the red, combinations of 2 choose 2 for the white, and when you're done, you'd multiply them together and you'd still get the same thing. It's just a different way of doing it. But like I said, I think most students have an easier time with this. All right, that's it for today. Do some practice here, especially practice picking out whether it's a permutation or a combination. I guarantee that's going to be the part you'll struggle the most with, is just deciding which one is which. That's why I was practicing it. Have a good day.